Okay, so if you completed your warm-up problem, rewriting the function with only t, hopefully you're seeing that. We're going to take 80, we're going to break that half out. All we want is t on the outside. So what we're going to do is we're going to put our half here, and using our properties of a power to a power, we're going to slip that 1/4 on the half so we can see the 1/4 times t gets it alone. Then, if I really wanted to, which I do, because it's fun, I'm going to take 80. We're going to find out what is 1/2 to the 1/4 power. Maddie? 0.8409. Did everybody get that? 0.8409. And that's going to be to the t power. So we rewrote the whole a of t function. So we only have one exponent of t, and basically what we did is, this is a half-life of 4 hours, so what we did is we rewrote the whole function in terms of just time, not per half-life. So every hour, approximately 84.09%, it's a bad 9, of the amount of caffeine remains in your system. That's what that is. You just had to peel that out with your properties of exponents. Then, next, what we got going here, not there, we're in section 10.2. What we're going to do is we're not going to have you cut these out. On page 751, just look, you should have equations and functions, I think. You're going to match each equation with the graph of the function here, okay? And I'm just going to hit pause. I'm going to give you about 5 minutes to do these. The functions, equations are on the bottom. Just match the equation with the graph.
Go at it.
Okay, so when you are putting your equations on the bottom together with each graph, equations down here in the bottom, together with the graphs, go through, and I know graph A is going to be a decay function because it's going down. I know B is going to be a growth function because it's going up. C is going to be a growth function, and notice graph C is growing faster than B. D is another decay function. E is another decay function because the graph is going down, and that one's decaying the fastest because it's the steepest. And F is going to be a growth. So think of, when you're looking at these, think of f of x equals some a times b to the x. If b is greater than 1, it's a growth function. If b is between 0 and 1, it's a decay function. So the one that decays the fastest is going to be the smallest number for b, and the one that grows the fastest is going to be the biggest number for b. So as I come down here and I look at my functions, okay, I know f of x, this first one's going to be a decay function because the 2/3 is smaller than 1. I know 0.1x, or 0.1 to the x power is going to be a decay. F of x equals 10x is going to be a growth function. 3x is going to be a growth function because the b is greater than 1. 1.5x is going to be a growth function, and the 1/3 x is going to be a decay function. So when I look at all my growths and or decays, I'll look at the growths first. This is a b value of 10. This one has a b value of 3. This one has a b value of 1.5. So the b value of 10 is the biggest. So I'm going to look up on top, and which one is growing the fastest is going to be the 10x. So I have a growth function here. I have a growth function here, and I have a growth function here. Now, f is growing the fastest, so this one needs to probably be the f of x equals 10 to the power of x because it's the steepest going up. The second one, notice graph C is not growing as fast as, or is growing faster than graph B. So graph C is going to take the next b value in line, that is in the next biggest one. So graph C is going to be my f of x equals 3 to the x, which leaves this one to be my f of x equals 1.5 to the x power. Okay, so all I have are my three decay functions now, and I got to see my b value here. B is 2/3. Here, b is 0.1, which is actually equal to 1/10, right? Think of a fraction. And my other decay is my b equals 1/3. So the one that is the smallest is going to decay the fastest. So which one of these is decaying the fastest? I've got E, and I've got D, and I've got, is it A? A is my last one? Yes. So you can see D, or E, I'm sorry, E is decaying the fastest. It's the steepest downward going. So therefore this one has to be my f of x equals 0.1 to the power of x. The next one, D, is not decaying as fast as A. So this one has to be my f of x equals 1/3 x, which leaves f of x equaling 2/3 to the x. Right? Woohoo! Got it. Moving right along here now. Analyze exponential growth and decay functions. Okay? What points do all the graphs have in common? What the heck do all these graphs, what points do every one of these graphs have in common?
It hits the y-axis at 1.
Yes, they hit the y-axis at 1. So the y-intercept is always going to be 0, 1. They all have that y-intercept in common when I'm in the form f of x equals a times b to the x. Now, here my a value for all these, a equals 1. As soon as a changes, that y-intercept is going to change, and it's just going to move up with it a little bit. Okay? And the reason why they all have these in common is because anything to the power of 0 equals 1. So just think of it just like making ordered pairs. If I made an XY chart here, if I knew A was 1, that means I'm looking at B to the X. If I came across with an X and a Y, if I put 0 in for X, I really don't care what B is, because B to the power of 0 is going to be 1, so they're all going to have that y-intercept of 0, 1 in common when A is 1. Okay? Compare the equations of the 6 functions you just sorted. What differentiates exponential growth from decay? We already talked about that, right? So when we are looking at a function, exponential function, f of x equals a times some b value to the power of x, if b, I'm going to move that down, if b is greater than 0 but less than 1, it's decay. Okay? If b is greater than 1, it's growth. Okay, so you should always be able to look at your exponential functions and say, hey, growth or decay, and figure those little buggers out really quick. So now we're going to do a little comparison here of Sarah and Scott's teacher asked them to each write a rule that would determine whether a function was exponential growth or decay based on its equation. Okay? So Sarah's obviously right because she got the thumbs up. Scott obviously was the bonehead in this spot here. And why is Scott's reasoning incorrect? What did he do? Well, he made a small assumption. Okay? It's growth if b is greater than 1. That's true. Okay? But it's exponential decay if b is less than 1. Not true. Okay? So if I said b is less than or equal to 1, that leaves a whole bunch of numbers open to it, right? That means I can put in 0 or negatives, and that doesn't work. My b can never be a negative number. If my b is a negative number, this is going to be my counterexample here. So if I looked at f of x equal, let's say, negative 2 to the power of x, if b, here b equals negative 2, if that's true, as I make my xy chart, if I put in 0, negative 2 to the power of 0 is 1. But if I put in a 1 now, I'm going to get what? Negative 2 to the first power is negative 2. Now if I put a 2 in there, what's negative 2 squared? That's going to be 4. If I put a 3 in, negative 2 to the third power is negative 8. So what we see here is we see an oscillating behavior. This is a big word for me to spell, so I got to look. Oscillating behavior. What that means is as I'm looking from a graph, what that means is if I had 0, 1, and then I point 1, 1, 2, I come down here. Then when I put in 2, I get 1, 2, 3, 4. I'm up here. And when I get 3, well, heck, now I'm way back down here. And it's oscillating like this. Okay, that is not an exponential function. Exponential functions either grow or they decay. They do not oscillate between positives and negatives. Make sense to you there? Okay. So, let's check out here. For what b values for the function in the form f of x equals b to the x produce neither growth nor decay? Okay? b equals 1 does not produce growth or decay. It's pretty obvious when you look at it. Okay? Think if f of x equals 1 raised to the power of x, okay, that's a constant function, right? That's just a constant function. It's a constant function for all real numbers. It's just the line y equals 1. Is there another number? 0. If b equals 0, okay, that also is not an exponential function, because now if you think f of x equals 0 to a power, okay, what the heck do we get? Well, first and foremost, you'll learn this later on in math, but if I put a 0 in there, 0 to the power of 0, it's one of those special cases. It's not 1. It's actually undefined. Okay, 0 to the 0 is undefined. 0 to the power of 1, 2, or 3 or anything, well, those are all 0. What the heck happens if I put a negative 1 in for x? Well, heck, now I have 0 to the negative 1 power. Remember what negative exponents do. That is going to make me look at my fraction, which means I'm going to have 1 over 0 to the first, which also is undefined. So all my negative numbers down here will give me an undefined. So I have a constant function for values greater than x when it's 0, but it's constant, therefore it's not growing or decaying. Those are the only two values that will not give us exponential growth or decay, b being 1 or 0. Okay. Number 5 here, okay, write an exponential function with the given characteristics. Don't overthink these. We'll be writing some a little bit different. But all we want to do is we want to picture out, they're not giving us too much. They're giving us one reference point. I know it's increasing from negative infinity to infinity. So that means I am picturing a graph that is going to look like this. So it starts and then it's always increasing. It's always going up. Now I also know that it's going to go through the point, this is a bad example, but it's going to go through the point 1,6. Okay? 1,6 should actually be higher than that. So when we're writing our equation, just think f of x equals a times b raised to the power of x. Okay? If I let a equal 1 here, because they only gave me 1 point, I'm going to let a equal 1, so now I'm just thinking f of x equals b to the x if I let a equal 1, and that's fine. Now I know that when I plug a value in here, I know that when I put a 1 in for x, it's going to spit out a 6. So what the heck does b have to be? Yeah, it would have to be 6. So I would have to say f of x equals 6 to the power of x. This is an exponential growth function because b is greater than 1. And it also goes through my point 1 comma 6. No? That would be one example. There's going to be a lot more examples you could use on that, but I think that's the easiest one to think of. When I look at b, now this one's a little bit different. This one is decreasing. This one's decreasing over the entire domain, negative infinity to infinity. That just means this one's going down. That means decreasing means b has to be greater than 1. Whoa. I'm going to say b is greater than 0 but less than 1. I'm sorry, and over here, b had to be greater than 1. So, when I think the same deal here, but we're going to go through this point, negative 1, 4. Now I'm plugging a negative in. Again, let's let a equal 1. Okay, so let's look at this a second and let's say, hey, what the heck does b have to be when I have an xy table here? If I'm putting negative 1 in for x, so f of x equals b to the negative 1, what does b have to be in order to get a 4 out? And now I need to remember b has to be a fraction between 0 and 1. And remember what that negative exponent does when you plug it in. Okay? That negative exponent reciprocates. So let's think about f of x equals 1/4 to the power of x. So if I put a negative 1 in here, is 1/4 to the power of negative 1, does that equal 4? And it does, because that negative exponent makes me reciprocate it. So I'm going through the point they wanted me to go through. B is less than 1 but greater than 0. Therefore, here would be a quick equation under the criterion they're giving us. Now we're going to probably build into, here's 2 points your graph has to go through. We're going to do those differently, but we're not going to do those today. They're not too terribly hard. Okay? Last thing we're going to start here before we get into the other stuf is on page 775. These are all things, honestly, that you want to remember when you are looking at exponential growth or decay functions. Okay? So we're going to put growth in the first column. The growth, or the domain of an exponential function. A growth function grows like this, right? So when you're looking at that picture, does it make sense that the domain is all real numbers? It's always going up, right? I can put any x value I want in for b, and it will output any value for me, or particular. How about the range? Well, I think before I do the range, we want to talk about asymptotes. Yesterday when we did it, we saw that we had a horizontal asymptote at y equals 0. And when the caffeine was coming out of the guy's body, it never really reached 0. It got closer and closer. Hence is modeling a horizontal asymptote. If I have a horizontal asymptote on this graph that I'm never going below, my range has to be all real numbers greater than 0. And it's not greater than or equal to 0, They're all numbers greater than 0 because I'm not touching 0 on it. Just like the caffeine problem yesterday. Theoretically, you never get to 0 milligrams in your system. Intercepts, we talked about those on the 6 graphs in the beginning, right? We had a y-intercept of 0, 1. Notice these all have a equal 1 because they're not giving me an a value in there. As soon as my a value changes, my y-intercept is going to go to whatever a is, and we'll see that when we start graphing some more. End behaviors. This has been a little bit since we talked about end behaviors since our polynomials. That is, as x goes to infinity, f of x goes where? So as I go out to infinity, my graph is going up on a growth. So as x approaches infinity, f of x approaches infinity because the right side is growing. If it's left-hand behavior, as x approaches negative infinity, f of x is approaching what? So now as I'm going out to negative infinity on my growth graph, f of x is approaching what? It's approaching 0 from which side? From the top side, right? So remember we put a little plus in there for the top side for my end behavior. Intervals of increasing or decreasing. Bless you, that just looks at your graph. Does this graph ever stop going up if you read it from left to right? No, so my interval of increasing and decreasing, it's increasing from negative infinity to infinity. It never stops increasing in exponential function. They're always going up, no matter where they're starting from. Okay? Now when we look at our exponential decay functions, again, a here is equaling 1 for all the purposes of this right now. Well, the only difference between that is, I'm going to draw my decay function down here on the bottom. My decay functions start high and then they come in low. And yes, just like the caffeine was decaying in his system yesterday, it gets closer and closer and closer to 0, which means horizontal asymptote at y equals 0. When I'm reading my graph, it covers all the x's that are negative, it covers all the x's that are positive, therefore domain is all real numbers. What's my range looking at that little red graph down there? It's going to be all real numbers greater than 0 again, right? Or you could say y greater than 0 for both of these. I don't have to actually say y because I'm underneath talking about range, so I'm okay. Intercepts, same. We saw that from the first 6 graphs in the beginning. And behaviors are a little bit different now, though, aren't they, when I'm looking here? I can see as x goes to infinity, so as x approaches infinity, f of x, where the heck is f of x going to? F of x is getting snug as a bug in a rug to 0 from the top side. And when I look at my left-hand behavior this way, as x approaches negative infinity, f of x is approaching what? Infinity. It's going straight up or coming from the top down there. Intervals of increase or decrease, when I'm looking at this red graph here, is it obvious as you read it from left to right, that graph is always going down, so it's always decreasing. And it's decreasing beginning at negative infinity all the way to infinity. It's always decreasing. Exponential decay functions always decrease. Exponential growth functions always increase. So, I'm going to hit pause for a quick second. Okay, we're going to push a little bit further forward so we can do some of your homework over the weekend. So we're going to compound some dough. We're going to compound some money. Everybody likes money. Everybody usually likes this part of the exponential functions, okay? Helen's opening her first savings account. She's depositing $500. Suppose she decides a bank that offers 6% annual interest. If you find any bank that gives you 6% annual interest, get all over it, because they don't even pay a percent usually. It's usually a percent of a percent. So it's really not a realistic answer or example, but they're just showing us how to use formula or an interest formula, okay? So the interest can be calculated at the end of the year. So they're only paying you interest one time. Technically, banks pay you interest 4 times a year. Okay, so we're going to be building this equation. So if I have my account balance equals principal times 1 plus the rate raised to the time, this is my kind of simple, I'm not going to call it compounding interest, because it's only giving you interest one time. It's not, well, it is and it isn't. But we're just going to look at it. So all we're going to do is the principal she put in was $500. That's going to get multiplied. If they're paying you 6% interest, everybody, I'm pretty certain, notice, say 1 plus 0.06. Your rate always goes in as a decimal. And we're going to leave it in there for T years. Now, when we did... what the heck was it? We did like the value of a football that Aaron Rodgers had. There was a test question a while ago, and it increased so much percent for so many years. When we did that, you guys all wrote 500, and because it increased, you said my R value was 1.06 to the time, right? It's because I have to add that original 100% that I'm putting in, plus the interest they're paying me. That's where the 1.06 is coming from, okay? So this A of t function, I should have put my t up here too, A of t function, I can plug in an account. This is reflecting she only deposited money one time, never again, and she's just letting it sit for as many years as she wants to find out how that $500 is going to grow on its own, okay? So let's say she put that money in there. We want to know how much is going to be there in the end of 1 year. Well, that's basically finding A of 1. So that's 500 times 1.06 to the power of 1. If I type that into my calculator, I'm going to find out, I don't want approximate, so I need to type this in. I have approximations. I want the decimals, because it's money. I don't want to get hosed on any money. So I got my 500. I can't use this calculator. The calculator doesn't work for me. I'm still yours, jealous. That's okay. So I got to take my 500, unless somebody has it for me, 1.06, the first power, which means I don't have to write it. Oh, it is. It's not approximately. It's $530. Okay? So she makes $30 interest. Actually, realistically, in a normal bank, you'd probably get about 6 cents interest in a year on $500, at best. They don't pay that much. How much would she have at the end of 5 years? Okay, so that's coming back and saying, what is A of 5? Well, that's 500 times my 1.06 to the 5th power. So that is, when I type it into my calculator, that one's equal to $669.11 would be her account balance. Okay? Suppose the bank starts to compound interest at the end of every 6 months. They don't typically do it 6 months, they typically do each quarter. But let's suppose the bank is going to compound interest at the end of every 6 months, but they still are going to offer 6% a year. So how much interest would they offer per 6-month period? Okay. Well, they're going to take your 0.06, and if they give you money, or if they pay you interest every 6 months, how many times is that per year that they would be giving you, paying you interest? That would be twice, right? So we're going to divide our 0.06 by 2. And so what they're going to do is they're going to pay you 3% interest on the first 6 months. They're going to roll that interest into your account. And then the second 6 months, they're going to pay you 3% again, but you actually earn that 3% interest on the interest they paid you the first half of the year. That's what compounding interest is. Okay, so 3% every 6 months. Now what this problem is doing, as we turn to page 777, what this problem is doing is it's modifying an interest formula into the formula banks actually use to calculate your interest. Okay? So we have John, Betty, Joe, and Lizzie were asked to calculate the amount of money. Who's correct? Well, who is correct here? Well, John's correct. Betty's correct. I want Lizzie to be my banker because she's going to pay me way too much money. What did Lizzie do? Well, Betty, Joe, and John, what John did is he took his principal times his 3% interest for the first quarter, okay? So he got $515. Then he rolled that $515 and got paid 3% interest the second 6 months. So he ended up making another $15.40 the second 6 months. So at the end of a year, he got $530.45. Betty Joe knows a little bit more about interest formulas than John does. Betty Joe knows that if I take the principal, well, I'll explain this in a minute, but she came up with the same amount. Lizzie says, hey, if I take my $500 times 1.03%, what she's doing is she's finding John's first calculation of $515. And she's saying, yep, I get that twice a year for $1,030. That doesn't happen. They're not paying you your initial investment of $500 over again, nor did you deposit any more money. So she's multiplying way too much. So what does this bring us into? This brings us into the actual formula for paying interest at a bank. Okay? My account balance in terms of time. This is a long, ugly one, and I will define every variable. Okay? Comes from, rate of function in Helen's. I'm first going to write it. It's your principal times 1 plus the rate divided by n raised to the n times t power. And it looks really weird, Farkas, doesn't it? Look at her, she's freaking out back there already. Okay, P is initial deposit. That's how much money you're initially putting in the bank. Okay? This 1 is always a 1. The 1 never changes. R, that's going to be your rate as a decimal. Okay? The N, what the N is how many times per year interest is calculated. Okay? Technically, math likes to say it's the number of times compounded per year, but that simply just means it's the number of times they calculate your interest every year. Okay? And T is typically always time in years. Now it's important to notice that that N is in 2 places. It's in two places. So if we wrote Helen's savings account at the end of T years compounded N times, all we would do is we would say her $500 times 1 plus, she was getting paid what? 6% interest, right? She was getting 0.06. We're dividing that by N times she's getting paid. Remember, before we divided by 2, but what happens if they pay you more than twice a year? And that's getting raised to the N times T power. Banks typically pay you interest quarterly. Quarterly in a year would be 4 times, right? So typically you put a 4 in there. It just depends what they're going to grab for you. Okay? We are on to our final page, and we're done. This is a long, riveting video. Everybody's goring their eyes out with rusty spoons as we speak. Okay? Determine Helen's amount of money in the account at the end of 3 years if interest is compounded twice a year. If it's compounded twice a year, my account balance after 3 years, not 2 years, okay? I'm just going to write this in here now. She put $500 in, 1 plus 0.06. If it's getting twice a year, N is 2, times the N times T is 3 years, so that would be a 3. So in the end, I'm mental mathing a lot of these things in, okay? I'm going to take my 500 times 1 plus 0.06 divided by 2 raised to the 6th power. And when I plug that all in, we find out she's getting 597.03 would be her account balance. So in 3 years, she just made $97.03 just on interest. Okay? What happens if they do your interest monthly? Well, now I'm going to take my 500. That's 1 plus. She's still getting 6% a year. But now, if you're getting paid monthly, how many months are in a year? 12. So now N is 12. N equals 12 here. N equals 2 up here. And that's going to be raised to the 12 times 3. Because in 3, if they calculate your interest once a month, and there's 12 months in a year, and they go for 3 years, in the end, you're going to be getting paid interest 36 times. So that's how many, your exponent should reflect how many times you get paid interest over that entire span. Okay? When I let my fingers do the walking in my calculator, and they're real easy to type in to the Inspire calculators and stuff, because you can divide out the fractions and type the fractions and all that good stuff in. Now she's at 598.34. It didn't do an enormous amount, but if she's paid interest every month as opposed to twice a year, she's making more money, right? Because she's earning interest, she's making money on the money they paid her already. I'm sure most of you already know this if you've been in your financial lit class. Daily. Holy crap. What is N for daily compounded? How many days are in a year? 306. So this is N equals 365. So all I'm doing, it's the same formula. And this is a nice thing with the CAS formulas or the regular Inspires, 0.06. Now I'm dividing that by 365, raising it to the 365 times 3. That's my whole exponent. And when I type that little bugger into my calculator, I find out it's approximately $598.60. Okay? So when I'm looking at this, question of the day, and this is where we're going to pick up on Monday, pretty obvious. What effect does the frequency of compounding have on the amount of money in her savings account? Shocking. Shocking, right? The more frequent her interest is calculated, the faster her money grows. Okay? So getting through here will allow you to do the front page of that yellow worksheet. The back page, most of that, I believe, if memory serves me correct, is going to bank off of what we're doing on Monday when we hit what's called continuously compounding interest. So, thank you for your attention. Have a great weekend.